Let's look at problem 8.1-14 of your text, which gives you data on how far snails travel depending on whether they're infected or not. It's a weird data set, but we'll go with it. Okay, so the first part A, says we want to look at the control snail group. So that's the second data set here that I have, so rows 5 through 7. And see whether or not it comes from an exponential distribution. It asks us to use the mean as an estimate for theta. All right, so let's do that first. Let's take the average of that data set. And we get 113.3226. So we want to group the data into 5 classes or 10 classes with equal probabilities. We'll just do both because we can. So I'll put 5 classes over here, and I'll put 10 classes over here with equal probabilities. All right, so the first thing we need to do is compute the class boundaries to represent the 5 different classes in the first case and the 10 different classes in the second case. So remember from class today, we solved the cumulative distribution function for the exponential to be able to get those class boundaries for a particular percentile, if you will. So if we remember, that was negative theta, and theta is up here in, let me not do that right now. Let me put in the probability. So we want 0.2, 0.4, 0.6, 0.8, and 1. I suppose we don't need the 1, but I'll put it in there anyway. All right, so this will be negative theta, which is here. I'll make that an absolute cell reference. Multiply that by the natural log of 1 minus the probability that we want. So let's copy this down this way, and we get those class boundaries. Okay, so with the 5 classes, we'll have something between 0 and 25.2872. Then between those 2 digit numbers, those two numbers, and then finally bigger than 182. So the first one will be count if our range of data is less than the number that's in B12. The second one, we'll use the count ifs command. We want to know if the data are, how many of the data values are greater than that 25 one, and also less than that 57 value. Notice again on here, I want absolute cell references on these 2 because I'm going to copy this thing down to the next 3. All right, so grab that and copy. Then for the last one, I just need the count if command. I don't need to worry about references, whether they're relative or absolute in this case, because I'm not copying it anywhere. And I want to know if that's greater than that last number. All right, so these are, let's see, make sure we have the right number of data points here. 13 and 11 is 24, and 7 is 31. If I go up here, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 22, 31 data points. Good, we got them all. All right, so this is our, I want to move this 10 classes over a bit. And maybe I'll move it down here. I don't know, I need to put it somewhere. This is our observed column. This is our expected column. This will be our observed minus expected squared over expected. These are equal classes with equal probabilities. So the expected number should be the total number, which is 31, times the 0.2, which is the probability of being in a particular class. So each of these numbers will be the same, the 6.2, which is exactly what it says in the stem of the problem. Not a huge surprise. Just if we were just doing it ourselves, we would still need to calculate the 31 times the 0.2 to get the expected number in each class. All right, observed minus expected squared divided by expected. Grab that and do that for all 5 classes. Get our test stat. We add these up. Critical value. All right. We use our chi-squared inverse function to get the critical value to compare to. I'm sure we're going to use alpha equal to 0.05 because that's what we always use apparently. Degrees of freedom. Well, there's 5 classes. We lose a degree of freedom because the last class is determined. 4 classes. We lose a degree of freedom because we estimated the average. So 3 degrees of freedom. There's our critical value. So we would not reject here, which is a good thing. We don't want to reject the null hypothesis. The null hypothesis is that the data are given to us by the exponential distribution. So we don't want to reject. And in fact, we want a high p-value. So to get the p-value for this one, we want the probability associated with being bigger than our test statistic on 3 degrees of freedom. And we get about 0.5, which is not so bad. Let's repeat the process, but using 10 classes here. So we'll go 0.1, 0.2 down to, really I only need 0.9, so I'll stop because I don't need to put the 1 in there because I'm not going to calculate the probability associated with that anyway. This is negative theta, make it an absolute reference, times log of 1 minus the probability. And drag. Those are the class boundaries, not including 0 at the top or infinity at the bottom. This one will be our observed column. This one's going to be our expected column. This is going to be our observed minus expected squared over expected. I'm going to just grab this text, copy the text down, and I'll change the B12 to be, what is it, B22. Okay. This one I actually have the I didn't just copy and paste because I didn't put the absolute cell reference on that first one. These actually have the absolute cell references on there, so I should be able to just copy and paste and give me that one, and then pull these down to get those. And then this one, I want to count if, scroll back up here, these, which ones of those are greater than this last value here. All right. Now, they already tell you in the problem that the expected value in each class is 3.1, but again, to figure that out, you would take the total number, which is 31, and multiply it by the probability, which is 0.1, to get that we really do expect to see 3.1 in each class. Observed minus expected squared over expected. Pull. Calculate our test stat. So we'll add up our computations from above. If we want the critical value, chi-squared. Let's talk about this one again. Alpha is 0.05. Degrees of freedom. We have 10 classes. We lose one, makes it 9. We estimated a parameter, makes it 8. So there's our critical value. Again, we don't reject. That's a good thing in these problems. We don't want to reject. So calculate our p-value to see roughly how good this is. So chi-squared. Here's our test statistic. And our degrees of freedom was 8. 0.37. So using 10 classes wasn't as good as using the 5 in this particular case. But again, not horrible. If you were using it as a model, it's not horrible. One of the reasons why we've got a bad one for this one is we've got this observed as 0. So we've got that bigger chunk there. That's actually the chunk in the middle is bad. We've got 6 in this class and 0 in this class, which is not very close to having the expected value of 3. So that's what's pulling our chi-squared statistic up and making it not necessarily as good of a fit as the previous one. All right, so that's how we do part A. Part B wants us to see if the data model a gamma distribution. Now they say use alpha equal to 2 and theta equal to 42. I want to do that a little bit differently because I actually want to use the data to give those estimates and not give what the problem says to do. This requires us to go back and remember stuff that we talked about back in Chapter 6, in particular Section 6.1, which is how do we find estimators for the different parameters for the gamma distribution. And if you look on page 279 of your textbook, you can actually figure out the what are referred to as the method of moments estimators for the two parameters for the gamma distribution in this case. So, according to the method of moments estimators, your alpha is going to be the square of the mean divided by what they refer to as V, and I'll tell you what that is in a minute, and the gamma is equal to this V divided by the mean. All right, so let's talk about what V is. Remember, we have a computation of the variance that is 1 over n minus 1 times the sum of the x of i's minus the x bars squared. Right, that's how we calculate sample variance. Well, the V is not sample variance. It's more like, it looks like a population variance. So the V is actually 1 over n times the sum of the x of i's minus your x bar squared. I know this looks awful in Excel, but I didn't want to switch windows on you. Okay, so this, remember, you're doing at each data point minus the mean, so that's what the x bar is, and then squared. So this is sample mean. And then we divide it by n. So this is basically using the population, treating it like it's an entire population rather than a sample. That's all the difference with the n in the denominator versus the n minus 1 in the denominator. Luckily, Excel calculates that for us. I didn't realize I had a typo up here for alpha. My apologies. All right, so when we do these then, I want to, for our alpha estimate, I'm going to use the average, the mean, of the infected snail data. I'm going to square that, and then I'm going to divide it by the var.p of that sample data, instead of using var.s. And yes, that's fine. So notice that really, if I use the data, my alpha estimate's 1.76-ish, not 2. That's why I wanted to actually use the data to do this. The gamma estimate is the population variance, the var.p, divided by the average of the data, which is 36.67. So notice that that one's even way farther off using a 42. All right, so yeah, I want to use the data to get these estimates. We could use the numbers that they gave you, but I really wanted to use the data so that we can see that and also talk about, again, how we lose degrees of freedom by estimating parameters. So, all right, we're going to have 10 classes in this one. Luckily, I don't have to try to find out, we don't have to solve for anything. This one's actually going to be built into Excel. The gamma inverse is built into Excel. All right, so here I'll do gamma dot inverse. The probability is here. The alpha is this one. I'm going to make it absolute. The beta is this one. Also make it absolute. And then copy down, just like we did previously. These are our class boundaries, except again with the exception of not 0 at the front and not infinity at the bottom. All right, so let's calculate our observes here. The first one's going to be count if our data are less than what's here in this column. Then I use the count ifs command for this one, highlight the whole thing, make it absolute. Is it greater than the lower bound? And I forgot the ampersand, which is why it just jumped on me. Greater than the lower bound and less than the lower bound, which is right next door. All right, and now pull to here. And I need one more. So I need the greater than one. So scroll back up. I need this data. And is it greater than that 129 number there? All right, there's our observes. Expecteds. All right. Expected again is we've done probabilities of 10% in each class. There's 39 data values, so this is going to be 3.9. Pull that down. Now do our observed minus expecteds over expected. I have no idea why that did that. That's just weird. That, oops, it's probably because I didn't hit the equal sign. Equals that minus that squared over that. And now pull to copy it all the way down. The test stat is the sum of those values. The critical value associated with this particular one. All right, using an alpha of 0.05 again for the hypothesis test. Let's see, we had 10 classes. We lose a degree of freedom automatically. That's 9. We estimated 2 parameters. That's 7. So the critical value is 14-ish. We would not reject. Again, to check our p-value. We use the chi-square again. There's our test statistic, 7 degrees of freedom. You get about 0.3. That's not the best p-value in the world, but it's not horrendous. It's just not the best. So anyway, that gives you an idea of how you can go through any of these by dividing it up into classes of equal width. We did this one for exponential, did this one for gamma. Just for grins and giggles, let's change these to 2 for alpha and 42 for theta, just to see what happened in the problem. I already referenced these particular cells, so it should change it automatically for me. So notice if I use 2 for alpha and 42 for gamma, my p-value gets a little bit better. It's about 0.4, which is not bad as far as trying to give a model for a particular probability distribution for given the data that we have. So anyway, I just wanted to go through this particular one so you had another example of how to do this. So when you're expected to do this on your own, next week when I give you some homework, you'll get a little bit better idea of what's going on. So until next.